Good afternoon, everyone, and welcome again in the second season of our reporting. And for today's topic is the heating capacity. Let's start out. First of all, let me explain what is calorimetry. Calorimetry is used to measure the amount of heat transferred to or from a substance. To do so, the heat is exchanged with a calibrated object. This object is called the calorimeter. The temperature change measured by the calorimeter is used to derive the amount of heat transferred by the process under study. So let's have one example to fully understand what is calorimetry. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. Always remember that calorimetry is used to measure the heat of a reaction, and it is a crucial part of thermodynamics. Okay, let's talk about the equations below that is related to the heat, temperature, and heat capacity. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times change in temperature for that substance. Or more practically, the heat exchange is equal to the specific heat of the substance times the gram substance times the change in temperature. These equations will be further explained later. So about thermal energy, what's up with temperature versus heat? Heat versus temperature. Heat describes the transfer of thermal energy between molecules within a system and is measured in joules. Heat measures how energy moves or flows, while temperature describes the average kinetic energy of molecules within a material or system and is measured in Celsius, Kelvin, Fahrenheit, or Rankine. It is a measurable physical property of an object, also known as a state variable. Other measurable physical properties include velocity, mass, and density, to name a few. To fully understand the difference of the two, I'll give you an example. We can start in temperature, like the day outside today. It might be hot, it might be cold. The example of heat is friction, which is why your hands warm up when you rub them together vigorously. Another example is you can measure the temperature of a room by placing a thermometer in the room and measuring the ambient air temperature. You can add heat to a room by turning on a space heater. As the heat is added to the room, the temperature rises. Heat and temperature are a closely related topic, and as such, the difference between the two can be a bit confusing. But always remember, the core difference between the two is that heat deals with thermal energy, whereas temperature is more concerned with molecular kinetic energy. You know the SI unit for temperature is Kelvin, so K equals C plus 273. Why did we get a 283 Kelvin? Because of 10 Celsius plus 273 is equal to 283 Kelvin. Now next is C equals to K Kelvin minus 273, and again 10 Kelvin minus 273 is negative 263 Celsius. Thermal energy is the total of the kinetic and potential energy of all the particles in substance, which means the energy contained within a system is responsible for its temperature. The perfect example of thermal energy is boiling water on the stove. Thermal energy relationships. As temperature increases, so does thermal energy, because the kinetic energy of the particles increase. If the temperature stays the same, the thermal energy in a more massive substance is higher, because it is a total measure of energy.
Heat, the flow of thermal energy from one object to another. Example, cups gets cooler while hand gets warmer. It is an example of an energy that transfer from one object to another. Heat always flows from warmer to cooler objects. Example, ice gets warmer while hand gets cooler. Specific heat, C sometimes S, but usually C. Things heat up or cool down on different rates. Example, land heat up and cools down faster than the water, and aren't we lucky for that? Specific heat is the amount of heat required to raise the temperature of 1 kg, but in chemistry we use grams instead. Of a material by 1 degree, C or K, they are the same size. C, water, is equal to 4,184 J kg, holds its heat. C, sand, is equal to 664 J kg, less E to change. This is why land heats up quickly during the day and cools quickly at night, and that's why water takes longer.
Why does water have such a high specific heat? Water has a higher specific heat capacity because of the strength of the hydrogen bonds. It requires a significant of energy to separate these bonds. Water molecules form strong bonds with each water molecule, including H bonds. So, it takes more heat energy to break the bonds. Metals have a weak bonds. Remember the C of E and do not need as much energy to break them. Q is equals to M times delta T times Cp. Q is equals change in thermal energy, and M is equals to mass of substance. Delta T is equals to change in temperature, Tf minus Ti. Cp is equals to specific heat of substance. Sample specific heat capacity table. Specific heat capacities of some common substances. Substance: lead, gold, mercury, silver, copper, iron. Specific heat capacity: 128, 129, 138, 234, 387, 448. Substance: glass, aluminum, wood, steam, ice, water. Specific heat capacity: 837, 899, 1760, 2010, 2090, 4184. If 25.0 of aluminum cool from 310 degrees Celsius to 37 degrees Celsius, how many joules of heat energy are lost by the aluminum? So we got the formula. Heat gain all over by loss is equals to Q and equal to specific heat capacity times mass times change in temperature, where the change in temperature is equals to final temperature minus initial temperature. So we have here our solution. Q is equals to 0.899 J all over by G times K. We got the 0.899 in the specific heat capacity table of the aluminum. Then 25 grams times 37 Kelvin minus 310 Kelvin. It was stated that we need to subtract both the final temperature and initial temperature. So let's input the solving in the calculator, and we've got the final answer, which is negative 1635.67, or if we round off it, we've got the Q is equals to 1636 joules.
Now I'm going to give you an example of specific heat. Number 1, it takes 487.5 joules to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius. So, what is our specific heat in joules per gram per Celsius? So, the missing here is the specific heat. Now, we're going to solve it by using the specific heat formula. Our specific heat formula is this. So, I already given. So, Q is heat energy, M for mass, C for specific heat. And the last, change in temperature. So now I'm already given the formula. We're going to proceed to the solving. So our Q is 487.5 joules equals our mass is 25 gram. So we don't have specific heat, so we're going to leave it, then proceed to this change in temperature. Our change in temperature is 75 degrees Celsius. We're going to subtract to the 25 degrees Celsius. So 487.5 joules equals to 25 gram. So we're going to subtract them. So we have a 50 degrees Celsius. So now we're going to multiply them. So 487.5 joules equals, so the answer is 1250 joules per Celsius. We're going to divide them. So 487.5 joules divided by 1250 gram per degree Celsius. So our final answer is 0.39 joules per gram per Celsius. So this is our final answer.
Here is another example. A 0.5 kilogram piece of aluminum increases its temperature 7 degrees Celsius when heat energy is added. How much heat energy is produced this change in temperature? In this problem, we are going to use the formula Q is equal to C times mass times change in temperature. Next step is first we are going to substitute the C, which is 0.899 joules per gram times K. Next is we are going to substitute our mass, which is 0.5 kilogram. And last is we are going to substitute our change in temperature, which is 7 degrees Celsius. And after we multiply our solution, we will get the answer 3.14.
On Earth, materials exist in one of three main states of matter: the solid, liquid, or gas. Materials can change between these states. When a state change occurs, a substance will also change. However, if the state change is reversed, the substance will recover the properties it had to begin with. Matter can transition between the three states when heated or cooled. When a material is heated, it absorbs heat energy. This additional energy can cause attractive forces between molecules to break. This leads to rearrangements of the particles because the attractive forces no longer hold them together as tightly. The same happens when a liquid is heated. The attractive forces between the molecules break, leading them to become more widely dispersed and a gas to form.
On this graph, it shows that the freezing point of a substance is the temperature at which a liquid turns to crystalline solid. The melting point is the temperature at which a crystalline solid melts. These are the same temperature, they just represent processes in opposite directions. As we heat a sample of ice, it will melt and then boil. On this diagram, the flat sections represents the phase changes themselves. In these sections, the temperature doesn't rise because the heat energy being added is going toward disrupting the lattice energy of ice, or overwhelming the hydrogen bonds occurring in liquid water. So during these periods, the heat energy does not go towards heating the sample. Once a phase change is complete, the heat energy returns to heating the sample. The energy exchange during melting and boiling is called the heat of fusion and the heat of vaporization, respectively.
So, if I want the total heat to take the ice and turn it to steam, I need 3 steps. First, to melt the ice, I need to multiply the heat of fusion with the mass. And the formula for that will be Q is equal to heat of fusion multiplied to mass. Then, there is a moving of temperature from 0 Celsius to 100 Celsius. For this, there is a change in temperature, so we can use the formula Q transferred is equal to Celsius multiplied by mass and multiplied by change in temperature. But wait, that just takes us to 100 Celsius. What about vaporizing the molecules? Well then, we need the formula Q is equal to heat of vaporization multiplied to mass. Add them all up and there it is. Now, lucky for us, just like there are other tables for specific heats, there are also tables for heats of fusion and heats of vaporization. At least we don't have to worry about that.
What quantity of heat is required to melt 500 grams of ice and heat the water to steam at 100 degrees Celsius? So I will given you the heat of fusion of ice, specific heat of water, heat of evaporization. So heat of fusion represents the amount of energy that it takes for a substance to change from its solid to liquid form. So our heat of fusion of ice is 333 joules per gram. Our specific heat of water is 4.2 joules per gram times Kelvin. Our heat of evaporization is 2260 joules per gram. Now that I already given it, let's proceed to the solving. How much heat is required to melt 500 grams of ice and heat the water to steam at 100 degrees Celsius? So our formula to melt the ice is Q equals heat of fusion multiply mass. We're going to multiply the amount of ice needed to melt and the fusion heat. I already given the heat of fusion here, so we can now easily solve this because the heat of fusion already have been provided. All we have to do is to multiply them. So Q equals the heat of fusion 333 joules per gram. And the mass is 500 grams. So the answer is 166,500 or 1.665. But we're going to round it off. It will become 1.67 times 10 raised to the power of 5 joules. So this is our answer for number 1. 2. To raise water from 0 degrees Celsius to 100 degrees Celsius. For the formula here, we're going to use the specific heat of water. So specific heat of water multiply by mass multiply change in temperature. Now we'll use the specific heat of water to answer this, multiplying the amount of ice required and the specific heat of water. So our answer is Q. Our specific heat of water is 4.2 joules per gram per Kelvin. 4.2 joules per gram per Kelvin. Then multiply the mass, as our mass is 500 and the change in temperature is 100. So our answer is 210,000 or 2.1 times 10 raised to the power of 5 joules. So this is our answer for number 2. So number 3 is to evaporate water at 100 degrees Celsius. So the formula here is Q equals heat of vaporization multiplied by mass. Now we're going to solve the evaporate water at 100 degrees Celsius. Yes, it is similar to the heat of fusion to solve this, but the only thing we use to solve is the given heat of vaporization. That is 2260 joules per gram. We're just going to multiply the amount of ice needed to melt and the heat of vaporization. So Q, what is our heat of vaporization? Our heat of vaporization is 2260 joules per gram. And our mass is 500. So the answer is 1,130,000 or 1.13 times 10 raised to the power of 6 joules. So this is the answer for number 3. Number 4, total heat energy. All we have to do to get the total heat energy is adding everything together. We're going to add the answer for 1, 2, and 3. You can use a whole number or decimal. So I'm gonna use decimal. So 1.67 times 10 raised to the power of 5 plus 2.1 times 10 raised to the power of 5 plus 1.13 times 10 raised to the power of 6. So the answer is 1.51 times 10 raised to the power of 6 joules.
Calorimetry is the science or act of measuring changes in state variables of a body, also known as measuring heats of reaction. In a constant volume or bomb, we burn a combustible sample from the heat change. We measure heat evolved in a reaction to get delta E for reaction. Some heat from reaction warms the water, which we know as the mass of water or C. This will lead to the formula: amount of heat exchange of water is equals to C times water mass times delta. Some heat reaction warms the bomb, which is known specific heat for the entire apparatus, so you won't be needing the mass. The formula would be amount of heat exchange of bomb is equals to heat capacity in joules over Kelvin times delta T. To get the total heat evolved, add the amount of heat exchange of water and bomb. The result will be the total heat exchange. Calculate the heat combustion of octane. C8 H18 plus 25 over 2 O2 towards 8 CO2 plus 9 H2O. You could burn 1.00 grams of octane, or you could just note that temperature rise from 25.00 to 33.20 degrees. Calorimeter contains 1,200 grams water. Heat capacity of bomb is equal to 837 joules per Kelvin. The givens are: C is equal to 4.184 joules per gram times Kelvin. Water mass is equal to 1,200 grams, and the delta T will be 25.00 minus 33.20 degrees is equal to 8.20 Kelvin. To determine the solution, step 1. Calculate heat transferred from reaction to water. Heat exchange is equal to 4.184 joules per gram times K times 1,200 grams times 8.20 K is equal to 41,170 joules. Step 2. Calculate heat transferred from reaction to bomb. Heat exchange is equal to 837 joules per Kelvin times 8.20 Kelvin is equal to 6,860 joules. Step 3. Total heat evolved. 41,170 joules plus 6,860 joules is equal to 48,030 joules. Heat of combustion of 1.00 grams of octane is equal to negative 48.06 joules.
If I burn 0.315 moles of hexane or C6H14 in a bomb calorimeter containing 5.65 liters of water, what's the molar heat of combustion of hexane if the water temperature rises 55.4 degrees Celsius? The heat capacity of water is 4.184 joules per grams per degree Celsius. Delta H is mCp delta T, which translates to mass times heat capacity times the change of temperature. Now it's equals to 5,650 grams of H2O, since 5.65 liters should be converted into grams, times 4.184 joules per grams per degrees Celsius times the 55.4 degrees Celsius. Now we have 1,310 kilojoules. Now this is not the final answer. We were asked for the molar heat of combustion. Molar heat of combustion, the amount of energy released in burning completely 1 mole of substance, versus heat of combustion, which is the amount of heat released per unit mass or unit volume of a substance when that substance is completely burned. We also have heat of fusion versus molar heat of fusion, and heat of vaporization versus molar heat of vaporization. So be watchful. What we calculated is the amount of energy generated when 0.315 moles of hexane is burned, which is close but not quite what we were asked for. We have this formula: delta H is equals to mCp delta T. M here is the mass in grams, Cp is the heat capacity of the water, and then delta T is the change in temperature. The mass given was in liters, so we need to convert it into grams. In 1 liter we have 1000 grams, so we'll have this, and then we'll just cancel the same thing, and then we'll be left with 5.65 times 1000 grams. Then we'll get 5,650 grams. Now we'll just fill in what's needed with the given terms. 5,650 grams of water is the mass. In grams, 4.184 joules per grams per degree Celsius was the heat capacity of the water, and then 55.4 degrees Celsius is the change of temperature. We'll need to multiply everything, and then we will get 1,310 kilojoules. The 1,310 kilojoules was not the final answer. It was the amount of energy generated when 0.315 moles of hexane is burnt. What we were asked for was the molar heat of combustion. To get that, we will need to multiply the 1.310 kilojoules by 3.17. We got the 3.17 by dividing 1 mole over 0.315 mole, which is the given mole of hexane. Finally, we'll get the final answer, 4,152.7 or 4,150 kilojoules per mole.